Okay, sorry about the interruption at the end of that video. What we were talking about is given a matrix M, given a matrix A that's m by n, then sometimes it's unclear whether we want to treat this as n columns in Rm or m columns in or m rows in Rn. So does it matter? And in one sense it doesn't matter, because what we're going to find is we'll double center the matrix so that if I sum down, I'll have zeros, and if I sum across, I'll also have zeros. Okay, so that's what we mean by double centering. And so the way we'll double center is we'll take matrix A, matrix A be given, then we'll compute the mean row. Let's call that R. So this is going to be a row vector. Then we'll compute the mean column C. So this is let's just make sure we see this. This is a row. This is a column. And then we'll compute the grand mean G. That is a scalar. Okay, and then we'll take our matrix A and we'll subtract it. I'm going to use an arrow so that indicates what we're doing here. We're going to take A minus the row minus the column, and then we're going to add in the grand mean. Now this notation would not be defined in linear algebra, right? What do I mean by this? Like this right here is subtracting this row R from each of the rows of A. And this notation means subtract this column from each of the columns of the result. And then finally we're going to add the scalar back into every entry of A. Okay? And in Python and in MATLAB, they'll both understand what this notation means, and they'll do it automatically, which is kind of nice. And you'll see, if you take a look at the code looks exactly like this. And the resulting matrix A, the new matrix, will have a mean of 0 in either direction. Okay, good. Now I should say that a lot of times it's obvious that we want our points to be in R2 or R3 or whatever, and so we'll just emphasize this, that if you're given a matrix like this that's like 5,000 by 2, then there's really no reason to double center this. Think of this as 5,000 points in R2, and so then you just have to subtract the row mean, write the mean down the 5,000 to get a 2 vector here, and then you would subtract that from each of the rows. Okay, and so that would just be your R, and so then you would take your A, right, take A minus R and then put the result back into A. Good. So that's pretty straightforward. Similarly, right, if you have a matrix that is 2 by 5,000, right, you also wouldn't really need to double center it unless there's something you have in mind. Because really, you see what's happening in the other direction, right? You would just be adding 2 numbers together. That doesn't really make sense to have to do that. Okay, so yeah, whichever direction, if it's not obvious, you would double center. If you have a 50,000 by 10,000 matrix, you may just go ahead and double center it. As we're going to see, it's not going to affect any of our statistics in terms of the variance. So you can go ahead and double center if you like. All right. Now, we've talked about the mean. I wanted to talk about measures of spread. And so that is the variance and the standard deviation. Okay, and so if we have a set of data, x1 through x, let's see, I'm using m data points in this case, then define x bar, right, as our mean, sample mean, k equals 1, I guess, to m xi. Good. And then we'll define the variance to be s squared, and that'll be 1 over m minus 1. So that's a little bit of a difference in what you might be used to computing. K equals 1 to m. Then we'll take our xk and we'll subtract the mean from that, and then square those results. So notice here that what you're doing is, if this is your x bar, right, you're taking your data and you're taking these distances that your data is away from the mean, and you're squaring those numbers, these distances. Okay, and then you're taking the average of those. Good, so you can think this is the average distance from the mean square distance. Okay, good, so that's one measure of the spread of the data, and that is the sample variance. Good. Sample variance is pretty straightforward to compute. On the computer there's usually the variance command. Notice that this is also the 2 norm of so if in other words, if I have a vector x that contains my values x1 through xm, right, then I would take my s squared could just be 1 over m minus 1 times the norm of x minus the mean of x. Good. Where norm is the command that you would, I should say squared. Otherwise we're going to run into trouble, right? Good. So that is the variance, and it's a measure of the spread. And the standard deviation, we should remember, maybe from our classes long ago, standard deviation. S is the square root of the variance, which is the square root of s squared. And that's why we're calling it S. Good. Okay. So, we don't do a lot with variance and standard deviation directly. However, we will be looking at things like a covariance matrix. And so we're going to be looking at how one data set also varies with another data set. And so some more computations that we want to make are correlation. And then we'll also take a look at the covariance matrix, because these are looking at how one set of data varies with another. Okay, and so in this case we'll go ahead and let x1 through xm be one set of data, and y1 through ym be another set of data. And I don't mean to say that these are unordered. These are ordered. Okay, so what we're going to be doing is we're going to be comparing x1 to y1, and x2 to y2, and x3 to y3, and so on. And so you don't want to mix that order up. And so the order here is really important. Good. We'll let x bar and y bar be the sample means. Okay, and then the covariance of x and y. Covariance of x and y, which we can write this way, or we could write covariance of x and y. Okay, is going to be defined to be 1 over m minus 1. Let's see, I've got m. I changed it from the notes for some reason. In the notes it's n data points instead of m. I'm keeping it as m data points here. Let's do the sum. K equals 1 to m of xi minus x bar times yi minus y bar. Good. So you'll notice right away that if x and y are equal, right, if you take x squared, that's just the same thing as s squared, right? That's just the variance of the data. Good. Otherwise, we get the covariance of the data. Covariance is sometimes hard to interpret on its own, and so we're going to take a look at the correlation coefficient, which is a little bit easier to interpret. But I don't want to get too far ahead of myself because we're at about 11 minutes now for this video. And so I'll stop here. In the next video, we'll talk about the correlation coefficient.